In the vertebrate retina, there are several different types of cell. The photoreceptors, called rods and cones, are at the back of the retina, and they transmit signals to bipolar cells, which in turn contact the large ganglion cells. These have long axons running across the surface of the retina and out along the optic nerve to the brain. There are also two layers of cells with horizontal connections in the retina. The horizontal cells, which pick up from many receptors and transmit to bipolar cells, and the amacrine cells, which receive signals from bipolar cells and transmit back to them, and sometimes also to ganglion cells. So light coming into the eye, focused by the cornea and lens, must pass through these layers of nerve cells before it reaches the receptors. It's possible to pick up signals from ganglion cells with a microelectrode lowered into the optic nerve inside the skull. Here, an anesthetized cat is fixed in a stereotaxic instrument, and I've introduced a microelectrode into the optic nerve coming from the cat's right eye. The cornea has a contact lens to protect it, and this lens in the spectacle frame corrects the optics of the eye so that images on a screen in front of the cat are in focus on its retina. The left eye is covered up. The electrode has been driven down, and now you can hear the action potentials from an optic nerve fiber on the audio monitor, and see them on the oscilloscope screen. We might expect ganglion cells to respond to flashes of light. So let's see what happens as we turn the room lights off and on. Off and on. There's a burst every time the lights go on. How are ganglion cells able to respond to flashes of light? We know from the anatomy of the retina that each ganglion cell receives messages from a limited group of receptors called the receptive field of the ganglion cell. Therefore, a small flashing spot of light will only stimulate a particular cell if it falls on the correct part of the retina. In other words, if it's shown in the correct position on a screen in front of the cat. So we can plot the receptive field with a flashing spot on a screen. First, we move a spot of light around on this television screen in front of the cat to try to find the right part of the visual field. You can hear bursts of impulses as the spot crosses one particular area. Now let's look in more detail at the responses to stationary flashing spots in this receptive field. You can see the visual stimulus on the television screen, where the spot can be moved about and turned on and off. Let's find out what happens when the spot is put in the middle of the receptive field. You can hear a burst whenever the light's turned on. This is called an on response and is usually indicated by a plus sign. Let's move the spot to another place and try again. On, off, on, off. Another on response. And now, further away, on, off. Notice that here the spot has a different effect. When it goes on, the cell is inhibited and stops firing. When the light goes off, the cell produces a burst. This is called an off response and is plotted with a minus sign. In this way, we can plot the whole receptive field. So this ganglion cell has a receptive field consisting of a central zone that produces on responses and a surrounding area that gives off responses. This type of ganglion cell is said to have an on-center, off-surround receptive field. It's interesting to see what happens when light falls simultaneously on the center and on the surround. Here are the on responses caused by a light in the central zone. Now I'll increase the size of the spot so that light falls on both the center and the surround. On, off, on. Obviously the response is much weaker. So light in the surround inhibits the spontaneous activity of the cell and decreases the response caused by a light falling in the center. This is why it's called an inhibitory surround. How are the center and surround of a ganglion cell wired up to produce this lateral inhibition? Each ganglion cell receives direct signals from a group of receptors via one or more bipolar cells. These rod and cone receptors form the center of the receptive field. Horizontal cells, picking up from the surrounding receptors, inhibit the bipolar cell and so decrease the activity of the ganglion cell. The function of the amacrine cells is not completely clear, but they too may play some part in this process of lateral inhibition. This is a diagram of the rods and cones seen end on from the back of the eye. Each receptor contributes to the receptive fields of a large number of different ganglion cells. So there is a great deal of overlapping of the receptive fields of neighboring ganglion cells, and these fields vary enormously in size. So far, I've only mentioned ganglion cells with on centers and off surrounds. These cells are directly excited by their bipolar cell inputs. But about half of all ganglion cells in the cat have receptive fields with off centers and on surrounds. They are inhibited by light in the center and excited by light in the surround. For both types of ganglion cell, the receptors in the surround of the receptive field have an opposite effect to those in the center. What's the function of lateral inhibition? Well, it means that ganglion cells respond much better to local differences of intensity than to overall illumination of the eye. On-center cells respond best to a white object on a dark background, while off-center cells prefer a dark spot on a light background.